Now this topic is on nuclear physics, and we're going to start off by looking at how the model of the atom has evolved over time. Now at the very beginning the atom was deemed to be a solid sphere, but then it evolved into something called the plum pudding model. And this is where electrons are scattered around. Now this plum pudding model suggested that you had a sphere of positive charge and then negative electrons scattered around the sphere. So this was a ball or sphere of positive charge, and these were negative electrons that were just dotted around the sphere. But this model was later replaced by Rutherford's model of the atom. And Rutherford proposed his model of the atom based on an experiment that he designed and performed. So what he did was he had a bunch of alpha particles, and Rutherford had a lot of experience working with alpha particles, so he knew these particles very, very well. And alpha particles have a charge of +2, as they are basically a helium nucleus. And what he did was he set up a piece of gold foil. This here is your gold foil. Around this he set up a detector. So this here is the detector that he set up around his experiment. What he observed was most of the alpha particles actually went straight through the gold foil and were undeterred. That was his first observation. Then he discovered that some of these alpha particles, in fact, were deflected by small angles. The third and final thing that he observed was that a very, very, very small number of these actually got reflected completely by 180 degrees. That was his third and final observation. So to recap on that, his first observation was that most of the alpha particles passed straight through the gold foil. He then observed that some of these alpha particles were deflected by small angles. Now, an even smaller amount, about 1 in 20,000 alpha particles, were reflected by angles greater than 90 degrees. So here's what he concluded about this data. He firstly concluded that atoms must be mostly empty space, and there must be a positive charge concentrated at the center, and also this center must be heavily dense. Or in other words, the mass of the atom must be concentrated in the center. And this is because the collision of alpha particles was elastic, and that the recoil speed of the foil was negligible. So this therefore must mean, to conserve momentum, there must be a heavy mass in the center. So it basically showed that most of the mass of the atom was concentrated in the middle, and this ultimately led to the discovery of the nucleus. So Rutherford's model ultimately proved the existence of a nucleus, which had most of the mass of the atom, and electrons would orbit this central nucleus. So with this Rutherford model, we can kind of estimate the radius of a nucleus. So let's imagine we have this alpha particle that is hurtling towards this gold nucleus at a speed of, let's say, v meters per second. And here's this gold nucleus with a charge of +63. And as you have two positive charges going to each other, you know that there will be a repulsive force by this nucleus, which will eventually cause this alpha particle to decelerate and come to a standstill, maybe at this distance here. We can kind of say that this distance here is roughly the radius of the nucleus. At this point here, we know that the kinetic energy of this particle is 0. Due to conservation of energy, we know that the initial kinetic energy is going to be equal to the final electrostatic potential energy between the alpha particle and the gold nucleus. And that is because we know that there is a electrostatic force of repulsion between the alpha particle and the gold nucleus. So we know that half mv squared is equal to kqq over r, where these two q's represent the respective charges of the gold foil and the alpha particle. And ultimately you could work out this value of r, which is actually known as the distance of closest approach. And it can be a rough way to estimate the radius of a nucleus. Now there is actually a much more accurate way of determining the radius of a nucleus, and that's by electron diffraction. So let's say we had set up this electron emitter right here, and we're going to use our nucleus as our slit. So our nucleus will be in there somewhere. And as you know, we should have a screen that we expect to see a diffraction pattern on. And this diffraction pattern takes its usual shape of a big central maxima and then consecutive maxima on either side. Well, firstly, we can work out the de Broglie wavelength of the electron using lambda is equal to h over mv. And we're actually going to measure this angle here between the first order minima and the central maxima. And if you remember, we know that n lambda is equal to d sine theta. Well, the order of our first minima is actually given by 0.61. So if we substitute 0.61 for m, we can get that 0.61 lambda is equal to d sine theta of our first order minima. And this value d here is actually r, which is our radius of the atom. So that is actually how we can accurately measure the radius of the atom. Now what we can actually find out is that the radius of our atom is directly proportional to the atomic number to the power of 1 over 3. And as you know, we can change this directly proportional sign to an equal sign by saying that r is equal to r naught, which is a constant, a to the power of 1 over 3. So r here is the radius of the atom, r naught is a constant, and a is your atomic number. And this is basically the number of protons in the atom.
Now, the best piece of advice I can give you after watching that video is to go off and practice some past papers or topic questions. These are single-handedly the best way to help you commit the content you've learned to memory. Obviously, go and do all the YouTube stuff of liking, subscribing, and if you found this video helpful, feel free to go and watch any of my other ones.